Good day, everyone. Today we are going to start with part 3 of chapter 1 solutions. We have already completed up till the solubility part. So, today we are going to complete the vapor pressure of liquid solutions. So, when a solute will be mixed up in a liquid solvent, liquid solution is formed. We already spoke about the solutions of gases in liquids. A solution can be formed either by two components liquid or a solid and liquid. And when we speak about liquid solute and solvent, they are volatile in nature in comparison to solid liquid solution. Hence, the liquid solution will have a remarkable vapor pressure. So now we will study about what is vapor pressure. So at a certain amount of heat, when we take a liquid in a closed vessel, and a part of this liquid will be converted into vapor phase and fill up the space available in the closed vessel. So, as the evaporation will proceed, the number of molecules in the vapor phase will slowly increase. So, the number of molecules which are present in the vapor phase will slowly increase. So, the molecules start to move randomly. And they will collide with the surface and again condense back into their liquid phase. So, hence, equilibrium is established in this closed vessel. That is, evaporation and the condensation will happen at the same rate. So, by this, we can understand vapor pressure. So, the vapor pressure is the pressure exerted by the vapors above the liquid surface in equilibrium with the liquid at a given amount of temperature. So, what pressure the vapors will apply on the closed vessel is known as the vapor pressure. So the factors affecting vapor pressure, first one is the nature of liquid. So if it has weaker intermolecular forces between the molecules, then the liquid will have a greater vapor pressure because the bonds will easily be broken and it will convert into vapor phase more faster, and hence will increase the vapor pressure. For example, ethanol has larger vapor pressure than water. Moving to the temperature, if it increases, then vapor pressure will also increase. This is because the kinetic energy of the molecules will increase. Moving to the vapor pressure of liquid solutions. When a binary solution of two volatile liquids is placed in a closed vessel, then both the components will evaporate and finally reach a state of equilibrium in between the vapor phase and the liquid phase. So, the total vapor phase in such a case is the sum of the partial pressures of each of the two components. This is according to the Dalton's law of partial pressure. But the relation between partial pressure and mole fraction was further explained by Martin Rolt, who was a French chemist. He gave a quantitative relationship between the partial pressure and the mole fractions of two components. So the Rolle's law will state that at a given temperature for a solution of volatile liquids, the partial pressure of each component of the solution is directly proportional to the mole fraction present in the solution. So, to understand this, we will consider liquid 1 and 2 and the mole fraction vapor pressure of these components in the solution. So, P0 is the vapor pressure of the pure component. So, we know that the vapor pressure of the component of the solution will be calculated with the following formula. So according to Dalton's law, we know that the total vapor pressure will be the sum of the partial pressures of each of the two components. So on further substituting the values, we will get the final equation to be this. This is a very important equation to be noted down. And then we'll study about Rolle's law as a special case of Henry's law. So according to the Rolle's law, the vapor pressure of a volatile component is given by the following equation. And according to Henry's law, the volatile component will exist and that the partial pressure of the volatile component is directly proportional to the mole fraction. And therefore, both the Rolle's law and the Henry's law become identical except their proportionality constants. And therefore, Rolle's law is a special case of Henry's law. Here is an ncert question which you people have to solve. Now moving to the vapor pressure of solutions of solids in liquids. So when solids will be mixed up in water solutions, then some physical properties of these solutions are quite different from the pure solvents. So here we have both the pictures, and the first one will represent the pure solvent while the second one represents 1 mole of solvent mixed up with 1 mole of solute. So if a non-volatile solute is added to a solvent to form a solution, the vapor pressure will depend only upon the solvent. There is nothing to do with the solute in reference to the vapor pressure. And the vapor pressure of the solution is found to be lower than the vapor pressure of the pure solvent at the given same parameters observed. So here we will observe more vapors molecules, while here we will observe very less because some of the surface will be covered with the solute particles. So you can understand that the decrease in the vapor pressure of the solvent depends upon the amount of non-volatile solute present in the solution irrespective of its nature. So if the solute may be sucrose or urea, it will not have any impact on the vapor pressure. The amount is only essential to understand how much will be the decrease in the vapor pressure. Now moving to the graph. Here the graph is between the vapor pressure on the mole fraction of the solvent, and this graph has the proportionality constant equal to the vapor pressure of the pure solvent at its peak. And we can conclude from this graph that if a solution obeys Rolle's law at all the concentrations, then its vapor pressure will vary linearly from 0 to the vapor pressure of the pure solvent. Now we will move on to the liquid-liquid solutions. These can be classified into ideal solutions and non-ideal solutions. First we'll speak about ideal solutions. So these are the solutions which obey Rolle's law over the entire range of concentration, and therefore they are called the ideal solutions. And the enthalpy of mixing of pure components to form the solution is 0, and the volume of mixing is also 0. So the above two property will mean that there is no heat observed or evolved when the components are mixed, and also the volume of the solution is equal to the sum of the volumes of the two components. So why is that they're actually not forming any variation is due to the interactions, that is the solute-solute, solvent-solvent and the solute-solvent interactions are all equal. Some of the examples are provided below. Moving to the non-ideal solutions. So these are the solutions which will not obey the Rolle's law in the entire range of concentration, and the enthalpy of mixing of pure components to form the solution is not 0. It can either be positive or negative. And the volume of mixing is also not 0. The volume may increase or will reduce after mixing. And the vapor pressure of these solutions are either higher or lower than that is predicted by the Rolle's law. So if the vapor pressure of these solutions is higher than that predicted, then it will give us the positive deviation. So positive deviation is observed if the solute-solvent interactions are weaker in comparison to solute-solute and solvent-solvent interactions. And the enthalpy of mixing of pure components to form the solution is found to be positive because there is a strong AA and BB bonds and they are not easily broken, while we have a weak AB bond which can easily broken and consecutively heat is absorbed, and the volume of mixing is also positive. Some of the examples are provided. Moving to the negative deviation. So negative deviation is when the vapor pressure of these solutions is lower than that predicted by the Rolle's law. So here the interactions are like the solute solvent interactions are more stronger in comparison to solute solute or solvent solvent interactions, and the enthalpy of mixing of pure component is negative. This is because the AA and BB bonds are easily broken while the AB bond is found to be stronger. So consecutively the heat is evolved and the volume of mixing is also negative. Some of the examples are provided. Depending upon the range of the deviation which is observed from the Rolle's law, a new category of binary mixtures known as azeotropes is formed. So now we'll speak about azeotropes, which are the constant boiling mixtures. So the binary mixtures having the same composition in liquid as well as the vapor phase, and that they boil at a constant heat. In such cases, they are not possible to separate using fractional methods. There are two types of azeotropes, which are the minimum boiling azeotropes and the maximum boiling azeotropes. So the minimum boiling azeotropes are the non-ideal solutions which show large positive deviation from the Rolle's law at a specific composition. So for these type of solutions, there is one intermediate composition for which the total vapor pressure of such a solution will be the highest and the boiling point will be the lowest. An example could be ethanol and water. So on fractional methods, they give a solution containing 95% by volume of ethanol. After achieving this composition, no further separation occurs as the liquid and the vapor phase have the same composition. Moving to the maximum boiling azeotropes. These are the non-ideal solutions which show large negative deviation. So we can observe that maximum have negative deviation, minimum will have positive deviation, and that they form a intermediate composition for which the vapor pressure is the lowest and the boiling point is the highest. So the minimum boiling and the maximum boiling are quite opposite to each other. And one such example is that the azeotrope formed by nitric acid and water. So it has an approximate composition of 68% of nitric acid and 32% of water by mass with a boiling point of 393.5 Kelvin. So a question is provided. Let us see the answer to this question. So what is the question? The vapor pressure of pure liquid X and that of pure liquid Y is 25 degrees Celsius. At 25 degrees Celsius are 120 mmHg and 160 mmHg respectively. If equal moles of X and Y are mixed to form an ideal solution, then calculate the vapor pressure of the solution. This is CBSE 2023 question. So here we are provided with the vapor pressure of pure liquids X and Y. So We can easily find the answer because we already know the vapor pressure of pure solutions X and Y, and the mole fraction will be 0.5 because ideal solution and equal number of moles. So the total mole fraction for each component will be 1.5, and by using the formula we can easily find the answer to be 140 mm of Hg. So you have completed the vapor pressure of liquid solutions. We have studied about what is vapor pressure and the graphical representations we'll see in the ncert itself. We have completed Rolle's law, and we have completed the ideal and non-ideal solutions, and we have completed positive and negative deviation. Now we'll give a quick ncert reading and also complete the graphs. In this part we have started with the vapor pressure of liquid solutions, and we've also dealt with liquid in liquid and solid in liquid, and we've already seen the binary solutions of two volatile liquids, that is component 1 and 2, and we have found out their Rolle's law, and it is given by French chemist Francois Martin Rolt. And we've already completed all these, and we've obtained this equation as well, and this is the graph which is provided to us. In these graphs, the 1 and 2 provide us with the partial pressure of the components, and which is marked as 3 provides the total vapor pressure. So this is very important to note these equations, because instead of the mole fraction we are using Y in the vapor phase according to Dalton's law of partial pressures. And we also provided with some in-text questions and example questions. Solve them, and we've also studied about all of these things and the pressure and everything, and we also understood this statement. This graph is done, and we have already read about non-ideal solutions, positive and negative deviations, and in these graphs we can observe the first one is about the positive deviation, so we can observe the positive deviation, and the second one is about the negative deviation, and we've also completed this. And here this is represented because a mixture of chloroform and acetone forms a solution with negative deviation from Rolle's law. This will happen because the chloroform will form hydrogen bond with acetone, due to which a negative deviation is observed. So hydrogen bond is the cause of the negative deviation. And we also completed the azeotropes, the minimum boiling and the maximum boiling azeotropes, and the examples are also completed. So in the next part we'll wind up the chapter with the colligative properties and how we will find out the molar mass. So we'll complete all the 4 colligative properties in one go, and we'll wind up this chapter. Thank you so much for watching, and stay tuned so that we'll complete this chapter and come up with more videos. Thank you so much.